Okay, so no, I've lost everyone. Right, so we're sort of doing this historical tour of machine learning. And the ironic bit is we're up to stuff that I completely assumed you all knew when I did my dimensionality reduction talk. So maximum likelihood is basically reinterpreting these error functions as probability models. Now, maximum likelihood, we start with an error function like this, a quadratic error function. And what we imagine is that we reinterpret what's going on as that we're seeing data given by y, which is a function of x, being equal to this, again, this basis function plus epsilon, where epsilon is some noise. Now, I think that the history of the development of this idea of noise is fascinating, and really the main person is Laplace. He's the person that, I mean, I guess when you were a mathematician or physicist, whatever you want to call him in those days, you were interested in everything that was going on. So he's not only interested in probability theory, and he does this crucial work in the 18th century on deciding whether a dice is English or not, but he also is interested in what really I think has driven forward a lot of the research from Laplace, certainly within Europe. There's this nasty split between the UK and Europe, which is centered around Leibniz and Newton claiming priority for calculus. And Europe really, UK really loses out from that, because a lot of the really interesting mathematicians at the time are in Europe. And for example, you've got the Bernoullis and Euler, who were all sort of inspired by Leibniz. And a lot of what those people are interested in is taking this new understanding of physics and inferring things about the data. Newton doesn't really do that. Newton doesn't say, okay, now I've described how these things work, let's infer the mass of this and let's do all that. I mean, he does a little of that, but the people that really take it forward, I think in particular, are Laplace and Gauss. And Laplace is particularly interesting because they've got this problem, and in fact I've got this slide a few steps ahead, which is probably more interesting than the slides there. This is their problem. So they want to do, in effect, linear regressions. It may be non-linear, but we can think of it in linear regressions. Their basis is taken from Newton's laws. So they're often working with a sinusoid or a cosine basis that they solved Newton's equations for some planetary oscillation, and now they want to know what the right weighting of these bases are. So they are doing very often a linear regression system, but the basis there is physical. It's coming from an understanding of the universe. So they've got these two data points in the linear space. So these might be two observations. So Gauss is famous for predicting where this dwarf planet that astronomers had, well, an astronomer, I can't remember the name of the astronomer, had identified, Ceres, but it passed behind the sun and was lost. So there was this hunt to find Ceres again, and Gauss predicts where it should be a year later. And they look there and they see it. And the way he claims retrospectively, potentially in order to claim priority on least squares, he did it, is by least squares. So he's trying to fit the parameters of this orbit, inspired by Newton's equation, to some observations that the original discoverer of Ceres had made. So he didn't make the observations, he's just got these observations. Now, I can't remember how many free parameters there are there. There's probably the mass of the planet and a few other things. Some of them are known. But the basic idea is, in this case, let's assume this is our model. We've got two free parameters, the offset and the gradient. So we only need two observations in order to determine the gradient of the line and the offset. So we can fit our model with two observations. Annoyingly, the person who discovered series made more than 2 observations, which was very inconvenient. Because as soon as you get a third observation, their question then was, and this was a big debate, how do you deal with this third observation? Because you have 3 observations and 2 unknowns. So they did things like compute the parameter for every possible combination of observations and take the median. They didn't know that, they didn't believe, for example, in the mean. They didn't believe that if you just sum up a bunch of error-strewn observations, that you should get an answer that is better. Because they didn't know the principle that if you sum across variables, the variance reduces. They thought that's clearly a wrong thing to do. Philosophically, if you've got a series of measurements with errors, you should try and work with the measurements which have no errors. So you should pick 2 measurements, the one which have the best no errors, and you should fit those 2 only. And the way they sort of talked about doing that is fitting every possible combination of measurements and taking criteria like what the median values were from that, and then using the 2 sets that gave you the median values, these sort of criteria. So what were they missing? They were missing models of uncertainty. And I want to use this to lead into Bayesian inference later, but for the moment, because it's where you put the uncertainty that's key. This is an overdetermined system, sorry. It's an overdetermined system, and we're going to deal with an overdetermined system by introducing stochasticity. Interestingly, we're also going to deal with underdetermined systems where you may only have 1 measurement associated with linear regression by stochasticity later. But where we put them and what they're called somehow seems to be different. So with 2 unknowns and 2 observations, you've got these formulae here, and you learned how to do simultaneous equations and solve for M and C. The third formula leads to an overdetermined system. And here's the trick. Add a slack variable, as Robert might call it. So some unknown. This is a corrupting variable that comes from the fact that you're acknowledging that you're not taking account for everything that could possibly happen in your model. So you're not taking account, in the case of observations of planets, of the different motions of the atmosphere which may be corrupt, or perhaps some setup of your experiment which is wrong. And so this is the error, which is how things are departing from Newton's equations. So these bits would be representing Newton's equations in the series case, and these bits are representing all the crap that's happening that is not part of your model. Of course, we recognize that as noise, but it's really important to sort of go back to the beginning of what noise was and say to yourself, philosophically, what is it? Is it something that's independent? Not under this definition. This could be dependent errors. Yeah? It's actually, I think, for me, the best definition of noise is it's the piece of your system that you're not accounting for in your model. Yeah? Now, very often we then assume it's independent because we can't do much if we don't assume it's independent. We sort of have to do some more modeling of the noise. But I think it's nice when you think of the physics side of things, these are the bits of the system you're interested in, and these are the bits of the system you're not interested in. Yeah? So that's one way of thinking about noise. I'm not saying it's the only way. It's probably not the original definition of noise, but it's the way I like to think about noise. So the problem's solved by sampling these values from some distribution. And the person who thought about this so much was Laplace. But Laplace believed in a sort of maximum entropy-like idea. So Laplace sort of said, well, if I don't know something, I should assume it's uniformly distributed. And that's kind of a reasonable assumption. That's actually the sort of a maximum entropy style assumption. And it's great, but it doesn't work very well on continuous systems. So he'd applied this on discrete systems like coin tosses. He'd applied it to justify his choice of prior. And we still justify prior distributions in his Bayesian inference. He sort of said, well, if I don't know, I'm going to assume uniform. Now, people can argue against this assumption. There are many arguments against it, but it's, I can't remember, it's his principle of least something or other. Can't remember the name of it. But it's a reasonable thing to do, and it's effectively what maximum entropy is doing. Problematically, though, you can't assume uniform distributions across infinite spaces. So he spent an enormous amount of effort trying to build what they called error functions, which reflected these type of ideas. So they were all heavy-tailed error functions. They had quite complex forms. He sort of said, well, it should be uniform across this interval and then uniform across this interval. And he spent a lot of time constructing these things, very difficult. And then when he got them, fitting them to data was virtually impossible because he just had pen and paper. And I guess if it's whoever it is, whichever Le Frenchman who invented least squares, he just comes along and says, let's minimize the squared error. And actually, he doesn't motivate it from this error function point of view. And why Gauss is known for the Gaussian is all he does is plug these two ideas together. Laplace is the error function man that says, this is the principle of what's going on. The other Frenchman is the person that says, algorithmically, here's a reasonable way of doing it. And Gauss says, okay, if you make the error function this form, the Gaussian, then you get least squares. Now, ironically, in Gauss's paper, he does nothing to justify that choice of error function other than saying, if you choose this error function, you get least squares, and we know least squares works well, so this must be a good error function. So it's a sort of circular argument. And of course, I think it's Laplace who produces one of the earliest versions of the central limit theorem, which is the real sort of physical justification as to why this might be true. That if you have a bunch of errors, as long as they're variance limited and they're additive, you will eventually have a Gaussian error. So that's a good, a reasonable justification of a Gaussian noise model. And it's Laplace that first derives the Gaussian distribution in the context of Bayesian inference. It's Laplace that doesn't notice that it's a sensible distribution for the error function. He comes up with the concept of the error function, and it's Laplace that demonstrates, in effect, why the Gaussian might be an error function, but we still call the distribution a Gaussian. And Laplace gets that one which is just the absolute value of two things, which no one even knows it's called a Laplacian. So that just shows, you know, you can't win them all. Okay, so what does that mean in practice? Well, going back, we move with the error function. This is effectively what Gauss did. These basis functions were coming from understanding something about the universe, from Newton. The error function was coming from, I'm going to stick with Legendre on this. It was coming from Legendre. Minimize this error function, you get least squares. It's a simple thing to do. Harder, of course, for higher dimensions because they were doing matrix inverses. They were doing that stuff by hand. So for them, this was almost the easy part. The difficult part starts when you fit the parameters. For us, that's easy to do because we have computers. So we're imagining we're seeing data given by a Gaussian corrupted observation of the linear model. And of course, if that's the case, that implies that the data has a mean given by the linear model and a noise given by sigma squared, which I tend to write in this, this form here, which is a Gaussian likelihood. And if we make an independence assumption across all those data points, so this is crucial, this is what we're saying about our noise, is that it's independent for each data point. It's I already talked about this last time. You know, independence assumptions, people keep assuming, let me assume my data's independent. I think it's crucial to remember, and it goes back to that proof I gave about Gaussians, what happens in high dimensional Gaussians. You're assuming your noise is independent, not the data. The data's only independent given W, and that becomes much more explicit in Bayesian inference when you integrate out W. So this independence assumption is about your noise. It's about the bit you're uninterested in, not about the bit you're interested in. If your data was independent, there would be nothing to learn from it. There's nothing to learn in the noise. So the independence assumption is about your noise. And not all noises are independent, so there can be some problems there. But writing that in a functional form, we have it in this shape. And then we can move back to the error function by noticing that that term there doesn't depend on W. And we're mainly interested in W, so we'll get rid of it for the moment. We will obviously be interested in the noise, potentially. But then the classic trick is to say, okay, so that product over exponentials can move into be a sum over the error functions just by basic properties of exponentials. And finally, the one trick which we use all the time is to notice that the exponential, we can logarithm both sides to get rid of the exponential. Why do we do that? I think we do it, number one, we can. Why can we do it? You should know this. We're going to optimize this. Why can we optimize a log likelihood as well as a likelihood? Monotonic function. Perfect. We can do it. Why do we do it in practice? Well, numericals, actually, that's one reason. Yeah, I think we do it because it makes everything easier to differentiate. Products are difficult to differentiate. We've made a product, we keep making product assumptions, yeah? By taking logs is a way of making multiplications simple. So we take logs and we go from a product to a sum. And the log likelihood is basically a scaled version of the error function we saw in the first case. And it's Gauss that points that out for least squares. Yeah, probably it was a very readable paper, and he was a good presenter at the conference, and so everyone remembered him for the Gaussian and had forgotten about Laplace's contribution on, and de Moivre, who also comes up with the Gaussian before. Okay, so we often, and this is actually, Robert mentioned this as well, in nonlinear optimization, the convention is to minimize. So we do probabilists are optimists, they want to maximize likelihoods, but once they turn it into a log likelihood and it's some nasty nonlinear function, you typically minimize the error function. So we might put a negative sign in front to do that, and then we get something that is just a scaled version of our original error function. So that's the probabilistic interpretation of the error function. That's what a probabilist like me sees when he sees a quadratic error function. How does that differ philosophically from the empirical risk minimization framework? It's actually quite important how it differs, because an empirical risk minimizer will write down the same objective function. But is he saying something about the noise in the system when he writes that? There's a good shaking of the head there. What's he saying about?
Saying there's zero noise.
Well, yeah, I don't know. He doesn't ever say anything about the noise, actually. So he might not be saying there's zero noise. But when you write down an empirical risk, what are you talking about? What do you need to know that we haven't even mentioned so far? It's not the noise. What do I need to know, though? I need to know the loss. People talk about loss and likelihood in the same thing. They are philosophically distinct. Loss is the cost you pay for being wrong, which isn't necessarily the noise. And I'll try and give you a little example of that. This is my, it took me a while to think about this one. So I realized, because very often people who take the optimization perspective say, the optimization perspective is just using the likelihood as a loss. People talk about the likelihood as a loss, but that's a nonsensical, badly motivated philosophical idea. And it's important what the difference is. Where does the likelihood come from? It comes from trying to describe the portion of the system that you're not optimizing. So here's my little example to show why these things, empirical risk minimization, can be dangerous. I'll also give a little example to say why it can be better. So I own a lumber yard, and I sell lumber. And it so happens that the demand for lumber is heavy-tailed. Okay, it's got some sort of Laplacian or student T distribution. So if you look at what I want to do is predict the lumber demand according to temperature. I'm just making this up. So I have, and it turns out it's linear. Actually, we know it's linear. It's very odd that we know this, but somehow we know the right model is linear, but we don't know what the noise is. So the noise tends to be like this. Now, it also happens that I know how much money I lose if I chop down the wrong number of trees. And I happen to lose a quadratic amount of money. So if we look at the loss I'm going to make, it's the call a demand that we observe y, and my predicted demand, which we'll make is m times temperature plus c. That's the actual loss. That's how much I lose in money. But I know that the demand is heavy-tailed. Now, in this case, least absolute deviation is the right thing to do. Actually, to minimize something with that form, least absolute deviation, or something we also do is we actually, least absolute deviation is the Laplacian noise function. So it looks like that. It's heavier tailed, it's exponentially either side and symmetric. Yeah? We know that's the right thing to do because that's a better approximation for the noise. It's less sensitive to outliers. So, for example, it might go up there and ignore that point here. Probabilistically, we either think of that as a Laplacian noise model, or we could also think of it either the student T noise model, which has a nice sort of peak like that. It's heavy-tailed again. And thinking about the noise is the right thing to do. We haven't actually incorporated this knowledge of our loss. And in fact, if we focus only on the empirical risk minimization, and I think it's important that empirical risk minimization is one choice of loss you minimize. You shouldn't necessarily minimize the loss that is the cost you're paying. Empirical risk minimization is saying that that's what you minimize, but this is a situation where that's the wrong thing to do, because the fit of your function will be there, and when the real data comes out and this turns out to be an outlier, you're going to lose money and your lumberyard will go under. Okay, now this is a consequence of worrying about the loss when you should have been worried about the model. Now, as a counterexample to this, let me, this is my other example, I say to why you should worry about the loss and not worry about the model. So my counterexample is actually a classification example. And, well, actually, I think I have to make these guys, annoyingly, sometimes this example isn't true unless you sort of do something like this. The Bayesian solution lines up. So in this case, now we're going to fit, this is people without breast cancer, without, and this is with breast cancer, and this is without. And this is some sort of mammogram feature summary, and you have to classify, and you're only allowed to use linear classifiers, whether people have breast cancer or not. Now, there's an asymmetric loss, because if you classify someone with breast cancer as not having breast cancer and they don't go for a test, that's a massive cost. But if you classify someone without breast cancer as having breast cancer, they go for a test, that's a small cost. So even though this is a linear system, there's a good solution, which is to put either the decision boundary there or there, yeah? And then either classify these people as having breast cancer, as not having breast, either classify these people as having breast cancer or these people as having breast cancer. Obviously, if you can go nonlinear, you can do both. But we're assuming model mismatch here. Now, in this case, model mismatch is a very bad thing to do the Bayesian approach, because the Bayesian approach will say, overall, I don't know. And it will probably put down a decision boundary around here with very low weights. And so if you look at the probability for everyone, if you actually have to decide to make a classification and you do it, well, you know, you may end up, well, in fact, I think actually the worst case, that would be all right, actually, just out of luck. But the worst case would be where such that the decision boundary might end up being like that. Yeah? So in this case, you can't move. So typically Bayesians then move the threshold to try and get the probabilities of breast cancer right to do the loss. And you can't move this in any such way that you classify all the people with breast cancer correctly and actually save any time. The only way you can do it is classifying everyone as having breast cancer. And the reason this happens is because the model's incorrect. It's a linear model, and you're not taking into account the loss when you do Bayesian inference. Bayesian inference says right up front, I don't care about the loss. Why don't I care about the loss? Because you can prove, if you've got the correct model, that the loss doesn't matter, and you can deal with the loss later when you do inference. Now, in this case, when you've got model mismatch, that's clearly wrong. In this case here, though, where you've got the right model, we said that we knew it's a linear demand. It's clearly right. You never know the model, though. You never know it. So the two approaches are philosophically distinct. One is saying that I'm going to be inspired by the cost I'm paying and minimize that. And that's the right thing to do in this case, but the wrong thing to do in this case. So neither one is universally right. And actually, you have to be very aware of that. Don't confuse them and think that they're just doing the same thing with two different, philosophically they're distinct. Any questions about that? I think that's an important point. It took me a long time to realize that, actually.
I know in the next got the probability distribution over all the possible linear classifier, I think there would be like high probability for the right and high probability for...
That's an interesting, lovely question. Good, I'm glad you said that. So the question was along the lines of, let's look at the probability for all classifiers. Then, and I also, because I exactly thought this too. So you're saying that there should be high probability for classifiers living here and high probability for classifiers living here. And then like that, yeah?
Yeah.
Okay, so because the likelihood's log concave, I know that this is a convex problem. It has a unique maxima. So it can't be bimodal in this way. So this would be a bimodality across the threshold that somehow we've got two possible thresholds, and this threshold's unlikely, yeah? And if that was true, that would be great. But it can't be true because the likelihood is log concave. So we know that whatever the posterior is over the threshold, it will be some corrupted unimodal distribution. And what actually happens is the most likely location is in the middle. Another question there.
Yeah, okay, so it's sort of a follow-up. I mean, the way we use this model, we use them in the client-customer setting. You know, I mean, you described before. So we would obviously want to tell somebody if he has breast cancer or not. That's a relevant question. And you would get a distribution over if that person has breast cancer or not. And this effect, I know it's concave or so on, but you would still, it wouldn't. I mean, you would still get you cannot be certain if you have breast cancer or not answer, I think.
Yeah, and the answer would be like 50-50.
Yeah.
So you might as well have not run the model.
Yeah, but then you obviously know that you, at some point you made the...
Well, you don't, but you don't quite know that because there's some nasty situations where you might start becoming confident. Let me give you an example of where you become confident back to the regression case. So this is actually the easier example to see where this problem arises with Bayesian inference. So here I have a nonlinear function, and I'm going to fit it with a linear model mismatch. This is where all the problems occur. So I fit it with a linear function. What are my error bars for this linear function?
I'm a Bayesian, I don't know what error bars mean.
So what are my error bars for the gradient? If I want to know the gradient of this, or if I want to know the m and c for this function, I might hope that the answer that Bayesian inference gives me is, look, there's a lot of uncertainty and I don't know what m and c is. And you know, it will do with a few data points. But what it will also happen is as I increase the number of data that are used, and it becomes really obvious that this is a nonlinear function. So I got, you know, it becomes completely obvious that this is a nonlinear function. What happens with the error bars? The error bars are actually only dependent in the linear regression case on the number of data. The error bars for the gradient and the offset. And so you just end up with a collapsed posterior that collapses at the value of this gradient, and it becomes completely confident that that's the right gradient and offset. It will have a noise that says, look, and there's noise, because that's the bit. The responsibility for the mismatch between the model and data is with the noise value, as we saw earlier. So the noise will correctly say, oh, there's something weird going on here. But you will, as you see more data, instead of becoming bimodal or something, so in this case here, as you see more data, the same thing happens. What instead of, you know, for low data, you actually cover these two possibilities. But as you see more and more data, you become massively confident that the right threshold for this thing is right in the middle. Now you're right, okay, depends on the model. If you use a sigmoid, what you're sort of saying is if you use a sigmoid, the sigmoid class conditional densities, if you look along here, will be very sort of diffuse. In fact, they might even be 50-50. But if we get an even worse model, I don't know, like a threshold, we don't allow it to have that flexibility, you could get massively confident about the wrong answer as far as your model goes.
I wonder what expectation means with respect to model or with respect to loss. Is it different or the same?
Yeah. Good question. I'd have to think about that more, but I think that that's quite a good question. And Mike Jordan once explained this to me in about 20 minutes, and it all made sense, but I can't remember it. But the way he talked about it is philosophically, in the statistical learning theory framework, you're doing the expectations across all possible data sets. I think his point was, in the statistical learning theory, you're doing expectations across all possible data sets, and in Bayesian theory, you're doing expectations across all possible models. And the answer you end up with, if you do both, I think was his point, is the Bayes risk. And that's including the loss as well. But I'm a bit shaky on that. But it did make a lot of sense when, so Mike sort of described it as a split that actually can be re-reconciled. And he does it in, so the thing to do is not to listen to me, but to turn to video lectures where the Cambridge Summer School, where Mike's there. And actually, I think he does it in that lecture and describes what happens if you integrate out both. And then you recover. I think he claims that's the Bayes risk. And it's a nice, clear explanation, but I don't want to recreate it without having looked through it. So the right thing is somehow to do both, but you typically don't. So the Bayesian choice is, so one of the things I say is that I practice in the church of Bayes, but I don't believe in the doctrine of model correctness. Because the Bayesian choice is set up around this doctrine that if your model is correct, you don't have to care about the loss. And as a result, it's very formulaic. You just write down your probability function. And a lot of Bayesians would say, what Zubin would say is, okay, if your model's not correct, then make it more complex. I don't quite believe that you can always do that. Certainly, it just becomes less tractable. So, it's a nice formalism because it describes exactly how you should put everything together, but it's got this problem that you have to be a bit careful about any case where there's massive imbalance between the losses you pay for misclassifications when your model's incorrect. Conversely, empirical risk minimization, you cannot save this situation by regularization. That's one answer that's given. That, okay, you're missing, in statistical learning theory, there's a capacity term. Right? And the way you deal with that capacity term is you regularize. This problem is not solved by regularization. It's solved by weighting, as Robert talked about, the data points. You get an iterative reweighted least squares type solution. So where the modification to the problem occurs is weighting your data, not weighting your parameters, which is what regularization does. So this thing just, you can't do this in the standard statistical learning theory framework. So weaknesses in both approaches. Okay. Okay, so we've done that. So, okay, yeah. Common confusion. Bayesian is not named after Bayes' rule. What they used to call this, and Zubin also says this sometimes, is they used to call it inverse probability. And in some sense it's a better name because it describes what's going on. But really, the term Bayesian refers to the treatment of the parameters as stochastic variables. So how do we solve the overdetermined system? Well, okay, we'll come back to that. So this is why they call it Bayesian. So Bernoulli, Bernoulli appears at the time, I guess he's inspired by Leibniz, and he appears at the time when there's this split between UK maths. Apparently English people can be arrogant at times, so they were ignoring the continent somehow. And he's talking about what we call the Bernoulli distribution, sampling, I think he calls black or red balls from an urn, and what the probability of getting black and red is. And you've seen that before. And the probability is dependent on the number of red and black balls. And that's known somehow. That's like an epistemic uncertainty, not an aleatoric uncertainty. So the parameter of the Bernoulli distribution, in the way that Bernoulli describes it, is an epistemic thing you're missing. Okay? So Bayes considers something different. He says a ball lands uniformly across a table, and then I place a bar where that ball lands. And now I want to know where the next ball lands to the left or right of that bar. And he says, okay, so these are all landing right, and the probability of this landing to the right is given by pi. All landing to the rest is given 1 minus pi. Yeah? That's the same probability distribution, but the stochastic thing, which is the ball landing, you know, the thing you're sampling, the ball landing to the left or right, is also used to generate the parameter. So if you believe, even though we can think of this as epistemic uncertainty, if you knew everything, you would know where the ball's going to land, we're considering it's like the paper landing on the ground. Yeah, it's actually aleatoric uncertainty in the way we classically think about it. So because he sets this up, the parameter as a random variable, that was controversial to Fisher. And Fisher said this was Bayesian as an insult. But like many insults, I mean, they believed it was a good paper. They weren't, you know, but they said that that's a Bayesian approach. Like many insults, like the Tory party in Britain, Tory was an insult. It was adapted by the group, and these people are now called Bayesians. But it's not using Bayes' rule. It's treating a parameter which is epistemic in its uncertainty as no different from aleatoric. Now, philosophically, I have no problem with that, but Fisher did. The reason he has a problem with it because he says that that is a known thing and you shouldn't be putting distributions over it. Laplace did that as well, and all the physicists were operating. They justified maximum likelihood on the basis of a sort of Bayesian approach with uniform priors. They were very Bayesian about how they were treating their parameters. But that's the controversy. I think in machine learning, it doesn't so much manifest itself in that way. It more manifests itself in this way of I'm going to do optimization or I'm going to build probabilistic models. So you sometimes hear people who are doing maximum likelihood in a probabilistic model as being characterized as Bayesian. But from a statistical point of view, it's not Bayesian until they start integrating out parameters. For example, Bayesian networks are not Bayesian, ironically. It's a bad name because they're just a probabilistic model, and if you fit the probability tables by maximum likelihood, they are non-Bayesian, they are frequentist. They only become Bayesian if either you use them to place distributions over things that are parameters, that are epistemic in their uncertainty, or you make a Bayesian treatment over them and you integrate out the parameters, which are also thought to be epistemic in their uncertainty. So the reason parameters are thought to be epistemic is the idea is I'm sampling from a model which is something in the real world, and that is a known single thing. It's not a distribution across things, and in some sense you could find out about it. Bayesians don't believe, well, Bayesians don't make a distinction between epistemic and aleatoric uncertainty. And I could argue that until account. I don't think aleatoric uncertainty exists. I believe in Laplace, who said that if an entity could know the precise state of every particle in the universe, then you could predict the entire future. Okay, Laplace didn't know about quantum stuff, which messes this up. But in principle, I think, you know, as far as we're concerned, because I wasn't clever enough to do physics, that applies. I believe that all uncertainty is in equivalent epistemic uncertainty, that we're just putting, when we do it in this case, it's just really nasty epistemic uncertainty because of chaos theory. Yeah? That I can't, you know, so I'm just going to treat the initial conditions with a little bit of a distribution, and that leads to aleatoric uncertainty. Okay, so there's the ball landing. So how do we do Bayesian inference? Well, Bayes' rule says that the posterior distribution of a parameter, I mean, Bayes' rule can also apply to variables. So in the examples I was giving before in the dimensionality reduction lecture, the latent variables are variables, and frequentists have no problem with putting distributions over them, because they're assumed to be sampled for each one of you individually. If we're looking at your IQ, we're assuming that your IQ is sampled from a Gaussian, and then we're doing some mapping to some test you do, and then we're looking at posterior over that distribution. But the parameters that map, they're assuming are sort of known features, and so they're epistemic. So when I integrated over W, that's Bayesian, but integrating over X wasn't Bayesian, because they're variables. And it can be a really subtle distinction. I once had, when I was in Manchester, I met a frequentist statistician who was interested in some work I'd done on biological data. And we were being Bayesian about, it was cells, and in each cell, there was a sort of little chemical system going on in there, and we were being Bayesian about the parameters of the chemical system. And I sort of described what we were doing, and he said, and I said, we're putting a prior over the parameter of this chemical system, which is like the kinetic rate, the sort of thing Mark mentioned briefly. And he sort of said, yeah, that's Bayesian. You can't do that. There's only one parameter. And I said, well, actually, this parameter is the decay in the system. And it turns out that we're looking at a population of cells. And in the population of cells, the decay parameter is also, the concentrations is varying because the cells are of different size. So although the decay is a fundamental property, we don't know the size of each individual cell, and the decay rate is varying because of that. So the decay rate in every single cell in this population is different. Then it's okay, you can put a prior over these things. And it's the same model, but as you just subtly change what you're saying about the system underlying it, then he was either happy that it was a genuine frequentist model or unhappy that it was a Bayesian model. So, you know, okay, for me, I would just rather forget about it and put priors over everything if I can. I'm what I call a pragmatic Bayesian. A pragmatic Bayesian is someone who integrates until his head hurts. Okay? So you keep putting priors over things and you integrate them out until it gets too much for you and your head hurts. I would argue that Zubin and Radford are also pragmatic Bayesians, but their heads hurt a lot later than mine does. Everyone's a pragmatic Bayesian, because you could just keep going to integrate and integrate and integrate. At some point you have to stop, and that, to me, is when your head hurts. So you've got this setup where you've got a likelihood and there's some parameters in the likelihood, and what you do is you integrate, you get the marginal likelihood by multiplying by the prior and integrating over the parameters. And that also then gives you your posterior, and if you're interested in the parameters, you have a posterior distribution over the parameters. You don't make a decision until you then include loss, which comes at a later stage. So you've got a posterior of what's going on in the world. It's an uncertain, there's a whole bit of decision theory, but that comes after you do this. This is inference. And the fact that decision theory isn't coming in here is what led to that problem we talked about in classification earlier. How am I doing? It's 1:30. Okay. So that visually can be seen as a prior in an offset. So that's a prior over the offset parameter in a regression. That's a distribution in this space. Multiplied by a likelihood. This is the likelihood we've been using before. And that leads to, and that's not normalized in this space. It's normalized, this space is over C, and that is normalized over Y. Yeah? So this is not normalized in this space. It actually is in this case because it happens to be a Gaussian, but that's an exceptional thing. Typically that's not normalized. We multiply those two together and we get a posterior which must be normalized. So in this case the posterior has this form. It's dependent on the variance of our noise and dependent on the variance of our prior, and that's a very typical setup. So we start with some belief about what the offset is, we observe a data point, and when we get an updated belief. The key thing you can do with this, and since I'm slightly over time, I'll just try and get to the, I'm not going to do the EM stuff that I said I was going to do. I should have just left that out, shouldn't I? I think I've left out the intro slides to that too. The point I want to make, though, is, just before I finish, about philosophically what's going on here, is how are we dealing with the opposite, what's the opposite of an overdetermined system? Underdetermined, yeah, clues in the name. So let's draw our underdetermined system. We're going to do a linear regression on that. I love underdetermined systems. I love uncertainty. They don't expose the flaws in your Bayesian model. So if you have a regression, a linear regression, well, a regression, it's not even a linear regression. You apply a linear model in this system, you get a really good answer. How do you do it when you only have 1 point? Well, you have a prior over the offset, and you have a prior over the gradient. And what it means is you get a posterior that might say that I've got a mean here, and then all these different gradient systems fit. So if I look at the error bars, this is what I like about it. This is my sort of why Bayesian inference can work even though it shouldn't. If you look at the mean and the error bars, you get a posterior that looks like that is damn good even for a nonlinear system. Because all it says is it goes somewhere near the data. As soon as you see more data, that messes it up. And then when it turns out to be nonlinear, so here, if it was nonlinear doing that, your error bars would be fine. Seeing lots of data exposes the flaws in your model. Your posteriors collapse and you become confident about something that's not true. How are you doing this? How are you dealing with an underdetermined system? You're doing it with uncertainty again. So the answer for overdetermined and underdetermined systems is to use uncertainty. Before, we didn't know what the noise was, so we put, in effect, a prior over the noise. You could think of it as. It's seen as a likelihood, but it's a distribution of the noise. Here we're putting a prior over the parameters. Now at that point I can finish, but just to summarize my last point is, I do think of that distribution we're putting over the noise as an aspect of a model. I do think of this prior I'm putting over the parameters as the aspect of a model. And I don't really believe in this separation between likelihood and prior that most people like to talk about. I think this is just a model. And it's all dealing with the same thing. There's uncertainty in my parameters. There's uncertainty in my noise level. There's a model mismatch. Maybe that's the separation between likelihood and prior. One's about model mismatch. One's about dealing with uncertainty in the model. But classically, people don't see it like that. So you deal with the underdetermined system with priors over your parameters, just as you dealt with the overdetermined systems with distributions over the mismatch between your data and what the model says. And there, I should just ask if there's any questions. I've overrun slightly. Any more questions? I mean, actually, it's a good, I think I'm happy to listen a bit to see if anyone, because I've said a lot of things which, not everyone believes, and that's fine. You can disagree. So if you think anything I've said is wrong, I'm very happy to hear your comments or thoughts about anything I've said. Philip? Oh, sorry, yeah. Oh, yeah, go ahead.
So, optimal decision theory is not the solution to this entanglement?
You mean Bayesian decision theory?
Yeah, well...
Well, it isn't, because you've already messed up. Because it's fine if your probabilities are well calibrated about what's going on in the system. If your probabilities aren't well calibrated, you're then dealing with a broken estimate. Bayesian decision theory assumes you've got the right probabilities. And if you have the wrong model, you don't have the right probabilities. And I think that the right solution is probably to have kind of formalism that includes the cost of inference in with the inference process. But I don't know what that formalism is. But people do. Chris Holmes recently talked about it. But I don't think it helps optimal decision theory. It's like the other side of the coin, that now I've got the probabilities, I should make the right decision.
Well, obviously, like if your model is limited, like it doesn't work. And something like you were talking about, you can add more flexibility, but you don't want to do that. Why wouldn't you do that?
No, because my brain's not big enough. So the question was, can't I add more flexibility? And Zubin and Radford Neal can, but and I think also if you start dealing with something as complex as speech recognition, the production process for speech recognition. Generative process, and you want to do inference on that. The complexity of your model is immense. Very, very difficult to deal with.
I mean, a Gaussian process with, let's say, RBF kernel with really, really small variance is like all the flexibility you want.
Okay, so the question was, a Gaussian process with an RBF kernel gives you all, with a small variance, gives you all the flexibility you want. So provably you can show that a Gaussian process with an RBF kernel will fit any function in the limit of data. But I mean, one of the questions about when I talked about Gaussian processes, well, what happens when two data points are on top of each other? But the extension to that is what happens when two data points are very close together. And you're right that if you have so much data, I mean, it's the wrong model though, isn't it? I mean, no, I should just do it on here, shouldn't I? You're right, if you've got so much data that you can see, and this is but this is a frequentist thing, not a Bayesian thing, because the model's wrong. So let's say that your data overall is doing that, but then there's these little fluctuations like that. So you fit an RBF with a single length scale, and it was trying to do that. But actually, as you observe more data, even in the Bayesian case, so Peter Solich just studied this, your learning curves will be slower, but eventually when you see infinite data, it will come out with not that length scale, but the small length scale, and it will go interpolate exactly through the function at the limit of infinite data. But I rarely get given infinite data, so I sort of want to know what happens in the case where I've got less data. And I think, I'm not going to give you any proofs, but I think the danger is what happens is you get effects like this, these small fluctuations here, but you get a global effect like this. So this problem, okay, you'll have to account for it through noise, but if you don't account for it through noise, then it's indicative that your smoothness term is wrong. Your RBF is overly smooth versus to what's going on in the function. You only see that flaw. It's again, this is why I think that the saving grace is normally you don't see enough data to expose the flaws in your model. You only find out that you've decided the system is much smoother than it is in 1D where you've got a lot of data. If you've got sparsely distributed data, you don't even discover this flaw in the model, and it gives you nice error bars. But as you get data very close together, you get numerical problems, the data fit, you become overly confident about your error bars because the real smoothness is larger than that, the real smoothness is rougher than that, but you think things are infinitely smooth. You get that collapsing effect I showed you. So in the example I showed in the other lecture, that was the end result after only observing data here, 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 and here, yeah? So that error function, that smoothness was actually correct in this case, but you get this collapsing effect even if the smoothness isn't correct, and your error bars are much tighter than they should be. So Gaussian processes are a big help, but actually one of the problems when you work with them a bit, you've just pushed the problem to another level. And then the worst thing, so smoothness you can deal with Matern covariances and rational quadratic. The worst thing is jumps. Bam. Bam.
Yeah.
If you need to start putting those in as well. So then you need a Markov jump process on top of your Gaussian process. And they're difficult to deal with. So as you start adding in all the components you need to model what you really think is going on, the model becomes much more complex. And that's a headache for people that do Bayesian inference.
We have the epistemic uncertainty and the alloteric uncertainty that may be interpreted as epistemic. How do we account for uncertainty due to subjective decision, as in reinforcement learning?
I think that, okay, so that's perhaps an area I haven't thought about so much in Bayesian learning. There's a lot of subjective decision. So within the statistics community, the Bayesians and the frequentists have fallen out so much that they don't even go to the same conferences. So of course, you have to fall out over something, and so the Bayesians have fallen out over something. And what they've fallen out is subjective Bayesianism and objective Bayesianism. And objective Bayesianism, as opposed to objectionable Bayesianism, objective Bayesianism is when you think that there's a universally correct prior for an inference problem, and that everyone, that prior is shared. Subjective Bayesianism says, well, these things are just about belief. So where does the prior come from? That's a big problem for Bayesian inference. And in subjective Bayesian, you have this personal idea of your prior, which you put down, and that's specific to you. So it's still, I would say, that's interesting. I don't know the answer. One possible answer is subjective Bayesianism is pushing everything to be epistemic about all uncertainty, and objective Bayesianism is trying to be aleatoric about all uncertainty. I don't know. Fundamentally, I don't know. I don't know if I worry that much about it. Because in machine learning, I think we worry often about empirical performance. So I think the end answer to all these problems, you can spend a lot of time arguing about it, but the right answer is to have a community where everyone is looking at similar things, talking about it, and showing their empirical performance on data. So to that extent, I think it's an interesting question to which I don't know the answer, but perhaps the answer for machine learning is who cares, let's see who wins on the MNIST data. Or whatever, or in reinforcement learning, I think there's lots of open questions there. Let's see who can get a robot to make me a cup of tea.
Could you discuss maybe a little bit about the
Yeah, we're a bit over time, but yeah, I think probably no. If I did it, I would do it. I've already done too many things too quickly, and I would do it too quickly, given the fact that we're over time. But yeah, I think I probably I should have talked less about other stuff. Philip.
So I think you made a really good point about the fact that Bayesians always assume that the model is right, and I agree that that's silly. I think, maybe to temper that statement a little bit, I think a corresponding problem or a similar problem in the statistical learning approach is the IID assumption. So in your example with the cancer patients, we know that in reality no data point is ever or the data is never IID, just like the model is never right. So it's similar kind of problem.
Well, it's interesting. Do they actually make an IID? Empirical risk analysis is an interesting point.
So
where the IID, because what I was claiming, and maybe this reveals a hole in what I was claiming, is that statistical learning theory people don't make an assumption about the noise. So in that case, it's funny to then say they're making an IID assumption, but they must be making some assumption in order to write the expected loss down, and that must be where the IID assumption's coming in, that potentially that loss is correlated.
Well, they're assuming that the data they have so far is representative of the new data that's coming in. So
Yeah.
if you know that, like a simple example would be if you know that there's a trend in the data and now you're moving on in time, then that's straightforward to model for a probabilistic modeler. And
Yeah.
hard for someone who's
Yeah, in fact, that's a good point. Yeah, so I think one thing that's very powerful, so we just wrote a recent review paper for Foundations and Trends, which was looking at multiple output covariance functions, which some people call multitask learning or structured learning. It's got a million different names, but it's used in kernel methods and it's used in Gaussian processes. And myself and my student Mauricio Alvarez and Lorenzo, and I should say Mauricio and Lorenzo did most of the work, worked hard to pull together what the statistical learning theory view of these multiple output covariance functions is and the Bayesian view. And why I introduced that is because what Philip's driving at is that it's often clear for a Bayesian how you expand your model to say the right probabilistic things. So I don't like the term multitask learning because from a probabilistic point of view, it's just a more complex model. And in general, if I want to learn across different tasks, I just have to specify probabilistically how those tasks are related. But in the statistical learning theory perspective, they also do that. I mean, but they do it in terms of an optimization problem and in terms of the kernel function and similarities over kernels. So they don't do it probabilistically, but they do try and do it. They try and reformulate the optimization. Massey Pontil has done a lot of work on this. The fascinating thing about it, though, is that at the end, the solutions they come up with are very strongly related to the probabilistic solutions. They have probabilistic interpretations as well. And that's a very nice aspect of having all these perspectives in the same community. Because you can sometimes look at what the optimizing people are doing and saying, well, what's the probabilistic interpretation of that? And if it's non-obvious, you can learn something. And I've spent a lot of time doing that. So I don't think it's entirely true that they can't proceed, but it may be more obvious for a probabilist how to proceed. But sometimes I think, okay, that's true. To be a frequentist, you have to be much more imaginative than a Bayesian. Because you have to come up with optimizer each time.
I think it's actually very, very related to, right, so the Bayesian will expand the model until it becomes Inference, and the frequentist will expand the model until he thinks that it has IID, and then so on. So, right, so it's a very...
I think that, I mean, first of all, if you take the loss, you're really doing something that looks a bit like reinforcement learning because you have an agent which takes decision, and that's an extra point. So I think that if you wanted to really do it Bayesian, you would condition you would make a model for when people take decisions, and you will condition on a decision actually being taken. So you would say, I'm only interested in the parameters where the stereo probability is such that I could actually decide something. And I think that would actually give you the situation.
That's an interesting idea. I like that idea of, I haven't heard about that before, but I like the idea. I think, to paraphrase, the idea of including the decision process in your modeling is kind of an interesting thing. But I don't know much about reinforcement. Philip might want to comment. But yeah, that sounds interesting. I should say, it's not the case that Bayesians can't classify cancer data, or that frequentists can't model lumber demand. They're artificially simple examples. Yeah.
Is there any connection to generative versus discriminative?
Yeah, you know, generative versus discriminative. Yeah, is there a connection? Okay, to the extent, it's almost a different argument, but it overlaps. So the generative versus discriminative argument is basically, and I think Vapnik really kicked it off by sort of saying, if I have, this is the way you write it in Bayesian terms, if I'm interested in a classification, P of y given x, I shouldn't model P of y comma x in an effort to estimate, because that's a harder problem. Which seems fair enough, difficult to argue with. I think the counter argument is, if I know something about the generating process, like for example, if I think that the generating process is manifold based of y and x, it may be that it's easy to put that assumption in there, but not easy to put that assumption in there. So I don't think it's as clear cut as Vapnik made out, although he's correct in the sense that joint density modeling is harder than, well, he didn't even say conditional density, he said modeling the actual class decision boundary, which is even simpler. What do I think about it? I think that it's not that interesting an argument, just because it just seems like, to an extent, it's partially become about branding in fields where they apply machine learning. And I think it's more complex than when they simplify the argument in the way that they do. So you hear often in computer vision, people saying, so here's a vision problem, and the right way to model vision problems is generative. Blah, 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 and here's how I'm going to do it. Or they say, here's a vision problem, and the right way to model vision problems is discriminative. Now, I think my own feeling would be that discriminative sometimes has better performance, but the time when it has better performance is often when you've got an enormous amount of data. So if you've got very little data about a problem, then being able to encode things in a generative way about how images are created or how objects are formed is going to lead to better performance. So I think the answer isn't clear-cut. And to a probabilistic modeling person, the answer should be, well, you write down the model in the best form you think is possible, including as many assumptions as possible, and then you see what the answer, what bit you should be maximizing. I think it doesn't really matter. But so object detection, I think this argument is big. And for large data sets of object detection where they've got a lot of objects, I think discriminative modeling tends to do extremely well. But that involved an enormous amount of labeling. So potentially the right answer is a discriminative generative approach. And John Wynn at a recent workshop in the Lake District was pushing that. And I think it makes sense. It seems to me that like so many things, probably it's a combination of yes to both, and it's like politics. I'm Labour, so I believe this. I'm Conservative, so I believe that. But sometimes each side can be right, and just as in politics, branding is important in certain fields, and I think particularly computer vision, where they want to identify what they do, branding becomes important. So an argument occurs where there probably should be no argument. I think the right answer is it depends on the circumstances, what the problem is, and what your data is. But I'm sort of presenting a probabilistic perspective on the generative discriminative approach. I think it's less clear what the difference, what they mean in the case of a sort of optimization perspective. Yeah.
Connected to the previous discussion of optimization viewpoint versus probabilistic.
Yeah, I mean optimization, but to me, it's clear what a generative and a discriminative probabilistic model are doing. One's modeling conditional densities and one's modeling joint densities. I know what a discriminative model is in the optimization thing, where you're sort of conditioning on one thing to present a class boundary. I find it harder to come up with examples of, maybe, do you have examples of generative model in the optimization perspective? I think I can think of one that I might say, but you give me one if you can think of one.
Well, we can always have the probabilistic models, but train it using fancy optimization viewpoints. Right?
Yeah, but I think that then it's, That's why I think the split doesn't fall along those lines. It's characterized as falling along those lines because Vapnik very much led to an optimization style approach, and he was the person that characterized the split, I think, did most, and other people might disagree with it, don't know. But I don't think it really falls along those lines, and it is true that I think it looks like it falls along those lines because often when people say I'm being discriminative, they then use the SVM. But they could use a Gaussian process classifier and they would still be being discriminative. You know, they just happen, the SVM just happens to be a really good general purpose fast tool, so they don't use the Gaussian process classifier. So I don't think the split falls quite along those lines, but I don't think enough. I've read theses where they start talking about generative models and they say an X is a generative model, and I say, well, how's that a generative model? You can't sample from it. So I think K-means clustering is an optimization problem without necessarily an underlying generative, probabilistic model. But you could argue it's a generative model rather than discriminative, perhaps. I don't know. But how do you generate from K-means clustering? You just pick a cluster. So I'm not sure it's I mean, the answer from the probabilistic perspective is you should just do the right thing according to whatever the set of circumstances. But I think people make more of an argument because of this branding thing. You know, they want to discriminate between themselves, ironically, and other people in the same field. So I've overrun massively, but I think it's quite a good debate. There's been some good questions, so I'm happy. But you're all hungry. I don't know what the weather's like. Maybe it's good to go to the beach now. So maybe we should finish there. Thanks.